Right now, as you look at your screen, you're effectively blind.
Yeah, it sounds crazy, but it's true.
Like for about 50 milliseconds at a time, your brain is actually shutting off your visual processing just to prevent you from getting dizzy.
Which is wild, right?
Okay.
You think you're reading this text smoothly or just taking in a whole web page in one continuous stream.
Exactly. But biologically, your eyes are violently throwing themselves across the glass in these tiny micro jumps.
And your brain is just aggressively stitching those still images together, to maintain that illusion of continuity.
Welcome to the deep dive. The mission today is to completely deconstruct the mechanics of how you actually read and process digital interfaces.
Because that illusion is incredibly convincing. I mean, we have this deep-seated bias to believe that our conscious minds are totally in the driver's seat when we're online.
Right, we assume there's this clean, logical sweep, from the top left of a monitor down to the bottom right.
But human-computer interaction research shows us a biological landscape that operates entirely outside of our conscious control.
It really is an invisible architecture of attention. And today we're pulling from a stack of sources, everything from foundational 1960s psychology experiments to modern machine learning studies on eye tracking data.
Yeah, because whether you build software, design presentations, or just spend hours a day looking at screens, understanding this invisible architecture completely changes how you interact with the digital world.
Because you're making split-second visual decisions before your conscious brain even catches up. Okay, let's unpack this. What are the actual mechanics of sight here?
Well, the biological limitation we are dealing with here is called the saccade.
A saccade.
Right. A saccade is the rapid ballistic movement of the eye as it shifts focus from one point to another.
If it's fast, right?
It is actually the fastest motion the human body can produce. We are talking about a duration of roughly 30 to 50 milliseconds per movement.
Wow. Okay, so if the eye is flying blind for those 50 milliseconds, which the sources call saccadic masking, how do we actually take in a web page?
That's the catch. The information intake only happens during the pauses.
Okay.
And those pauses are called fixations. When the eye completely stops moving, the fovea, which is the tiny central pit in your retina that handles sharp, high-resolution vision, it locks onto a specific area.
And how long is a fixation?
Typically anywhere from 100 to 400 milliseconds.
Yeah.
It depends on how much you're thinking about what you're looking at.
So the smooth video we think we're seeing is actually just a rapid-fire slideshow.
Jump, pause, jump, pause. Exactly. Saccade, fixation, saccade, fixation.
But that biological bottleneck creates a huge logistical problem. Because, the fovea is tiny, right? It only processes a few degrees of the visual field in sharp detail.
Right, it's a very narrow spotlight.
So if the periphery is just a blurry mess, how does the brain know where to command the eye to jump next? It can't just be guessing.
No, it doesn't guess. It relies on something called covert attention.
Covert attention.
Yeah. The cognitive psychology research shows that visual attention is actually decoupled from the physical eye. Your attention is operating about 100 to 250 milliseconds ahead of your physical gaze.
Oh, wow. So think of covert attention as an invisible advanced scout. And the physical eye, the fovea, is the heavy infantry.
That is a perfect analogy. Yes,
Yeah.
the scientific consensus fully supports that.
So you open a document, your advanced scout darts out into that blurry peripheral terrain. It sees, I don't know, a dark cluster of pixels that might be a bolded word.
Or maybe a block of text that looks like a quote.
Right. And the scout signals the brain, hey, there's structural value over here. And only then is the heavy infantry commanded to swing over to that exact spot.
To resolve the high-definition details, exactly. Your attention is literally living a quarter of a second in the future.
That is mind-blowing.
And that advanced scout is navigating using a mix of bottom-up stimuli and top-down goals.
Meaning what exactly?
So bottom-up stimuli would be the physical properties of the screen. Bright colors, sudden motion, high contrast. Things that forcefully grab the retina.
And the top-down goals.
Those are your conscious goals, like you're searching for a specific price or looking for a submit button. The scout balances those two forces to plot its course.
Okay, so since the eye is just following the brain's advanced scout, what does this actually look like when we open a web page? Because it sounds incredibly chaotic.
Oh, it is. We rarely read left to right, line by line anymore.
We're not reading a digital article like a printed novel.
Not at all. We are actively foraging. Eye-tracking heat maps from groups like the Nielsen-Norman Group prove that, well, digital reading is basically a myth.
We just scan.
Right. We engage in very nonlinear information retrieval, and the most famous scanning behavior they've documented on desktop is the F-shaped pattern.
Right, the dreaded F pattern. Anyone in design knows this one.
Yeah. A user starts with a horizontal scan at the top. That's the top bar of the F. Then the eye drops down, does a shorter horizontal scan, and finally just does a strict vertical scan down the left side.
Wait, so if I write a brilliant conclusion at the bottom right of a page, no one sees it?
Almost certainly not,
Oh, why?
because the F pattern is actually a coping mechanism. It happens because of cognitive fatigue.
So it's not people being lazy.
No, it's what users default to when they want to be efficient, but the text lacks formatting cues. If there are no subheadings or bullet points, your advanced scout has no structural landmarks to look for.
It's just staring out at a featureless desert of text.
Exactly. So it falls back on the path of least resistance. It hugs the left wall, waiting for a capitalized letter or a number to break the monotony.
Which is inherently bad for both the user who misses information and the business who is trying to communicate. The bottom right is basically an anatomical blind spot.
Completely cold on the heat maps, the fovea literally never visits it.
But wait, everyone is on mobile now. Desktop patterns can't be the whole story. Does the F shape still apply on a phone?
The physical constraints of a narrow mobile screen actually force a shift. It leads to what researchers call the marking pattern.
The marking pattern, how does that change the dynamic?
Well, on desktop, the text is static and your eye moves around it. On mobile, the thumb takes over the navigation.
Oh, right, because we're scrolling.
Think of a ballet dancer doing a pirouette.
Okay.
To keep their balance, they use a technique called spotting. They lock their eyes on a single fixed spot in the room and whip their head around to anchor on that exact coordinate every time they spin.
The room spins, but the visual anchor is static.
Yes, mobile users are spotting the screen. The eyes stay focused in one static central place on the screen, usually the upper middle, while the thumb scrolls the text upward.
That makes so much sense. The eye becomes a stationary sensor, and the interface is just this flowing river of data.
It's super efficient, physiologically speaking. Using your thumb takes less cognitive effort than programming dozens of tiny eye jumps. But it does fragment your comprehension because you're only catching bursts of data when the scrolling slows down.
Okay, so that's text, but what about search engines? Because those pages are incredibly complex now.
Search engines are the perfect natural experiment for this. In the early 2000s, Google results created something called the Golden Triangle.
The golden triangle.
Yeah.
Because the results were just 10 blue links on a white page, right?
Exactly, highly linear. And the eye-tracking heat maps showed a heavy concentration of eye activity strictly in the top left corner.
People would look at the number 1 result, scan the title, drop to number 2, scan a bit less, and then click.
The whole right side of the screen was just a void. But modern search pages aren't like that. They have carousels, people also ask, boxes, knowledge panels on the right.
So the layout is actively rewiring our visual paths.
Yes. The Nielsen-Norman group calls the modern behavior the pinball pattern.
The pinball pattern, because our eyes are just bouncing around.
Exactly. You look at a link on the left, saccade over to an image on the right, bounce down to a video in the middle. Our eyes bounce chaotically because the brain is trying to evaluate the utility of different data formats at the same time.
The interface layout is actively commanding the saccadic rhythm.
Precisely.
Which brings us to a massive, ongoing debate in cognitive psychology. If the interface layout dictates where the eye goes, and we can track those micro movements, are we effectively reading the user's mind?
That is the million-dollar question.
Right. Can we reverse engineer human cognition from a gaze plot?
Well, there was a theory proposed in 1980 by researchers Marcel Adam Just and Patricia Carpenter. It's called the strong eye-mind hypothesis.
Okay. What did they argue?
They argued that whatever the eye is looking at, the mind is actively processing with zero lag. If you fixate on a word for 300 milliseconds, your brain is thinking about that word for exactly 300 milliseconds.
Here's where it gets really interesting, because what about when we zone out?
Yes. That is the huge biological flaw in their hypothesis. It's a phenomenon called cognitive decoupling.
Cognitive decoupling.
Your working memory can completely detach from your visual input. You can stare directly at a UI element like a submit button, while your brain is completely detached.
So the heavy infantry is pointing its weapons, but the general back at headquarters has left the building.
Beautifully put. You might be dealing with high cognitive load or retrieving a memory. A prolonged fixation might mean deep thought, or it might just mean you are incredibly confused.
The biometric data looks identical, but the mental state is completely different.
Right. But for decades, people assumed you could just read minds from eye tracks. And a lot of that stems from this legendary 1967 experiment by Alfred Yarbus.
Oh, the Yarbus study. The methodology here is intense.
It is. He used an invasive eye tracking mechanism involving suction cups attached directly to the subject's eyeball
Suction cups on the eyeball. Ouch.
and mirrors reflecting light to track the gaze. But the data was groundbreaking. He showed subjects a complex painting by Ilya Repin called The Unexpected Visitor.
And the painting has a lot going on, right? People reacting to an exile returning home.
Yes, lots of faces and emotions. Yarvis asked subjects to look at the painting multiple times, but he gave them a different task each time.
Like what?
Guess the ages of the people. Guess their wealth. Remember their clothing.
And the gaze completely changed based on the task.
Entirely.
Yeah.
When guessing ages, the eyes jumped exclusively between faces. When estimating wealth, the eyes scanned the furniture and clothing, ignoring the faces.
So Yarbus proved that top-down tasks dramatically alter visual search.
He did, but the scientific community took that and made a flawed assumption. They assumed that if the task shapes the scan path, then looking at a scan path should let us deduce the task.
Reverse engineering the thought process.
Exactly. But modern machine learning studies finally tested this assumption.
Right, like the 2012 study by Green and colleagues. They put this to the test with AI.
They did. They called the study Reconsidering Yarbus. They tracked eye movements of people looking at 64 complex photographs, giving them 4 distinct tasks, just like Yarbus did.
Memorize the picture, guess the decade, determine relationships, or determine wealth.
And then they fed all that rich, multidimensional biometric data saccade speed, fixation length, into a linear discriminant classifier.
A type of AI algorithm.
Right. And the AI was amazing at certain things. It could easily identify which of the 64 images was being viewed just from the eye movements.
Wow.
It could even identify who was looking at it because we all have idiosyncratic, unique eye movements.
Like a biometric fingerprint in our saccades.
Yes. But when the AI was asked to predict the observer's top-down task based on the scan path, it failed completely.
It performed at what, 27.1% accuracy?
Exactly. Which is basically just random chance for 4 options.
So the tension here is clear. Top-down tasks change how we look, but static scan paths alone aren't enough to decode complex human thoughts. The map is not the territory.
Precisely. You can't just reverse engineer intent from a heat map.
So if the eye is this unpredictable and easily fatigued, and we can't just read minds from heat maps, how can you, the listener, apply this knowledge today? Like if you're designing a presentation, writing an email, or building an app.
You have to design for the scout, not the infantry. You have to break the F pattern.
We must rescue readers from the F pattern. How do we do that?
You use what designers call the layer cake pattern.
The layer cake.
Deliberately using highly descriptive headings and subheadings, this gives the advanced scout structural landmarks.
So the eye can scan horizontally across those structural elements and only jump into the body text when it actually finds what it needs.
Exactly. And you pair that with the spotted pattern.
Which is bolding keywords.
Yes, bolding critical verbs or metrics inside the paragraph. It catches the eye's advanced scout by creating high contrast edges.
So instead of a wall of text, you're building a highly scannable landscape. What's the second practical takeaway?
You have to respect reading gravity.
Reading gravity. This is tied to the Gutenberg diagram, right?
Yes. In Western cultures, we read left to right, top to bottom. So reading gravity naturally pulls the eye diagonally from the top left to the bottom right.
It's like a biological momentum.
Exactly. The top left is where the eye instinctively drops in. The bottom right is the exit point.
So the top right and bottom left are weak fallow areas.
Very weak. If you put crucial information in the bottom left, you are forcing the reader to work against their natural reading gravity.
Which destroys their rhythm and comprehension. It's like trying to pour water onto a flat plate instead of a bowl. It just spills everywhere.
Beautiful analogy. It creates unnecessary cognitive friction.
Okay, takeaway number 3. Is there any way to override these patterns entirely?
There is one biological override that is almost undefeated. The face bias.
The face bias.
Even in cutting-edge 3D saliency studies, where people are looking at complex 3D models, humans exhibit an intense, undeniable bias toward facial features.
Because of the fusiform face area in the brain, right? We are evolutionarily hardwired to process faces instantly.
Yes. If you need to anchor attention on a busy screen, faces are an almost biological cheat code. The advanced scout will prioritize a realistic human face over almost anything else.
But wait, Earlier you said that just putting a smiling stock photo next to a complex data table is a terrible idea.
Oh, it's the worst idea. It's a cheat code for attention, yes, but it destroys utility.
Because the fovea jumps to the face. But then the brain spends its energy evaluating the face's emotion and identity rather than reading the data table.
Exactly. The face becomes a biological black hole. It absorbs attention and distracts the user from their actual task. You're trapping the advanced scout.
So you have to leverage the face bias very carefully, only when the face actually supports the message.
If we connect this to the bigger picture, human-computer interaction shows us that a screen isn't just a static page, it's a dynamic landscape.
Right.
Our eyes are proactive. They are constantly hunting for the next piece of information. They aren't passive receptors.
So writers and designers aren't just putting words on a screen, they are actively directing a biological symphony of saccades and fixations.
When we understand how the eye actually wants to move, we can stop fighting our biology and start designing for it.
That is beautifully said. Recognizing the biological machinery driving your attention makes the digital world look entirely different. Next time, we'll dive into how the specific colors glowing from those screens might be quietly manipulating your perception of time. You won't want to miss it.